All right, now we got assessing normality, 6.6. So basically what we're going to do here is we're going to talk about how we can determine whether data meets the requirement for normally distributed data, or basically whether the normal distribution is satisfied. One of the ones that we've talked about briefly before was a normal quantile plot. We're going to go into more definition of the normal quantile plot. What's really cool about it is basically that it is one way that we can capture whether data is normally distributed. As you see, these are three normal quantile plots. They're basically a pair of points. So you have an x value, and then you have a z-score that corresponds to that observed value. So these are paired data. It's a scatter plot. And then you notice this green line is a trend line, basically trying to figure out whether the data follows that green line. And that's very important to understand why that's going to be key here. You'll see that basically this is not normally distributed data. It's actually skewed. And then this looks more like normal distribution when we have data. And then you'll notice this one kind of has like this wave shape to it. And I believe this is a uniform distribution when we have that. So determine whether it is reasonable to assume. All right, so this is a histogram, right? These two graphs correspond to basically finding whether something is normally distributed or came from data that was normally distributed. So first you want to construct a histogram. Do that. If you don't have a lot of data points, then using a normal quantile plot is really nice. Reject normality if the histogram departs dramatically from a bell-shaped curve. Identify any outliers, reject normality if there's more than one outlier. And then finally, use a normal quantile plot. To me, you should always use a normal quantile plot and a histogram. Histogram first, right? See it? If there's not enough data, you definitely want to do a normal quantile plot. So, okay, so procedure for determining whether it's reasonable to assume the sample data are from there, right? Use the following criteria. Normal distribution, the population distribution is normal if the pattern of the points is reasonably close to a straight line, and the points do not show some systematic pattern that is not a straight line. So this, not good. That is not normal. This is like a normal distribution because it follows kind of a straight line pattern. Yes, you might say, this is a straight line here, straight up, and then straight over. Yeah, we want it to be straight, like follow a green line or something like that, right? Population is not normal if it deviates from that, right? Points do not lie reasonably close to a straight line, and finally the point shows some systematic pattern that is not a straight line pattern. So this is not a straight line pattern. Okay, this is a really good one where basically you have a histogram, and this is the corresponding normal quantile plot. If you can see it, basically follows it. Yeah, there might be a couple of like weird things here and here. Those could be considered outliers, but if you look here, what do we have? We have a couple of high values, maybe, you know, going out here, maybe above that. But other than that, looks pretty good, and I think it'd be safe to assume this is normally distributed. Now, remember how I said there's kind of like a pattern to that one, look kind of curvy? That's a uniform distribution. So, and this is why, for example, it's sometimes better to do a histogram because you'll see right away that that is not normal, not normally distributed. And when you look at this, you might be like, oh yeah, it follows a straight line real quick, and then move on. But really, it does, but it's kind of got a pattern to it, and that's why it doesn't work. And obviously, this is skewed, and this is positively skewed or right skewed. Histogram shows that. And then if you look at the normal quantile plot, yeah, looks like that too. So that's one way we can look at that. Again, these two are tied together because they both basically test for normality, which is really cool. Now, there's ways that we can construct these by hand, but it's better to just know how to do them in statistical packages. And if you watch one of my other videos, I have one about how to use our package that we're using, I think StatCrunch. So you can use that. If you're going to do it by hand, which I don't have anybody do that anymore, but there's ways to do it by hand, so you guys are familiar with it. So you can read over that if you'd like. But next thing to talk about is data transformations. So sometimes when you have data that doesn't look normally distributed, a lot of people do a log normal approach, and basically it means that you're logging the data to make it look more like a normally distributed values. If you want to use that, you're going to want to make sure that you read the literature that corresponds to that. Like if that's something that happens a lot in your field, then you want to look into that for maybe transformations to your data. But you can transform data to do that. And there are a couple other transformations you can do. You can do the square root of x, you can do 1 over x, or x squared. You can do a couple other ones. But again, I would highly recommend that you would be fluent in what you're field is doing for transformations. Sometimes they do it for population or time. They'll do a log approach, but yeah. And that's it. So let me know if you have any questions.